Welcome to our presentation about in-situ analysis for critical IoT systems. My name is Florian Schmidt, and together with Sören Becker and Professor Ode Kau, we are working on different kinds of technologies to help IoT systems. We are all working at the TU Berlin at the research group of complex and distributed IT systems. So let me introduce you to our research group. We have currently more than 20 researchers working in our group, and our key research areas are actually anomaly detection for cloud computing, IoT edge computing, but also big data frameworks like Flink and providing fault tolerance to all of these systems. We also give the lecture about cloud computing, for example, to the master course. So we have access to a lot of master students and supervise a lot of theses there. We also participate in the Berlin Big Data Center, the Daimler Lab, and Professor Kau is the chair of the Einstein Center of Digital Future. Infrastructure-wise, we have a huge HPC cluster, newly bought last year, costed more than 3 million euros. And we have also dedicated servers, more than 200, just for our group. You know, in our recent days, it's very difficult to meet and see each other. So I provided a picture from our website. This is one part of our group. And in the middle, you see our chair, Professor Ode Kau. And on the top, you see Sören Becker and myself, Florian Schmidt. We normally talk about public clouds right now. So AWS, Microsoft Azure, Google Cloud, they all provide some public cloud services which are consumed by, for example, smart homes right now. But when there are problems with the internet connectivity, or you need low latency, for example, for self-driving cars, we need some kind of other technology to cope with these problems. So here comes in the term of edge clouds. We have edge sites where we can also place compute power very close to the customer, so to a base station, or for example to a smart home. In 2018, 10% of the data is created and processed outside the public cloud. And in the next 5 years, Gartner predicts that this figure will reach 75%, which is a significant increase. So when it comes to cloud computing, the new enabler technology is 5G. So 5G is right now developing, and already in Germany you can get access to it. With 5G comes also the hope for low latency networks and a high throughput network. So we can send a lot of data through the network. This enables new, as I said, use cases like self-driving cars to move information from different cars together and give also information from the neighborhood to the cars. And for these kinds of new use cases, the demand is very high for reliable networks. And in this area, we try to help that we can help. In order to provide these kinds of demands or show that these demands can be ensured, we need some kind of KPIs for these service providers. So for 5G, we think in this area that edge computing is a technical enabler to provide such kind of KPIs. So based on the space technology of 5G, we hope together with edge computing, we can provide more use cases, more flexibility for new business opportunities. Of course, the whole infrastructure then increases very high in complexity. So we have a significant increase in complexity, and it's very difficult to check the overall reliability of this infrastructure, of course. here comes our main focus of our research, how to support the operation and management of these edge clouds. So this is called actually AI Ops. It stands for AI supported operations, especially for services and infrastructure to ensure reliability. But also we worked on a framework for decentralized analytics, which we show next. So for this decentralized analytics, we built up a fog computing testbed. On the right side, you see in blue the cloud layer. This is a public cloud scenario. So we have our public cloud installation, which is an open source project, OpenStack, running on our servers, but can be also AWS or Google Cloud. And inside there, you're running, for example, data storage or visualization or analytics, data analytics. So this is traditional, the cloud layer, but now we also have a fog layer. So at the bottom, you see sensors, which can be also actors. For example, light sensor, temperature sensor, camera modules. And they are connected to edge devices to send the data to the edge devices, which is our first computation device. We also include into the fog layer a gateway device, which is then capable of connecting to, for example, a public cloud. We assume that on all these gateway devices and edge devices, we can deploy a containerized management software like Kubernetes. In this case, we are running here different kinds of Raspberry Pis, which run K3s, which is a light-weighted Kubernetes installation. All these components are connected right now via a mesh network. We are using Batman here to provide the capabilities to send also data between these components, to place different algorithms at different compute nodes, but also sending them into the public cloud. To have a more clearer visualization here on the right side, you see from the last master project, a smart garden project, where we have some small greenhouses with a lot of sensors inside connected to a Raspberry Pi. We have a few of these greenhouses, and they are connected via the mesh network together and then sent through gateway nodes to our public cloud, which then does the data storage and the visualization. But we also aggregate some information directly on the Raspberry Pis. So in order to provide some technology for moving analytics in between these infrastructure components, we are using BitFlow. This is also a framework developed from our group. It's a lightweighted framework for real-time processing. It's capable of inputting a data stream, and then you can chain together different machine learning algorithms, for example, or different other kinds of processing steps. And these can be described through our BitFlow scripting language. For example, we have some kind of input data stream, which can be a TCP input or CSV file. Then we apply, for example, standardization, detect then anomalies, and then rewrite everything into a CSV file in the end. Behind these algorithms, there's different kinds of programming languages applied, like Python, Java, and Go. So each of the algorithms might be written in different programming languages and chained together. You can have a look at our GitHub page, where everything is open source available. Furthermore, then to distribute this chain of analytic steps, we have the BitFlow operator, which works together with Kubernetes. And as long as you have a Kubernetes cluster running, it can schedule the algorithms on demand and optimized for your needs. For example, for low latency or computational power resource usage. So here comes in our in-situ analysis for our IoT capabilities. We try to analyze specific algorithms directly at the edge. So this is our goal. And for example, we monitor here at one compute node our resource consumption, then normalize the data and do some aggregation to have lower bandwidth usage through the network and do then more complex stuff like clustering or other machine learning algorithm on another host. Also, when we would put here more cost problematic algorithms directly at host 1, then also the monitoring data will change as we are consuming more resources, which we don't want to do. So our current research focuses right now on optimizing the placement of these algorithms and with respect especially on resource consumption and locality, for example, the latency. So I want to show you an evaluation, the quantitative evaluation of computation costs. We have here a commodity server with 8 CPU cores, 3.3 gigahertz, and a Raspberry Pi 4B, the latest version, with 4 CPU cores, 1.5 gigahertz. And we apply 3 different algorithms on both of these devices. And based on the IFTM framework, which is an anomaly detection framework, which also includes forecasting algorithms like online ARIMA and LSTM, but also online clustering algorithm like CA Birch, which is also developed by our group. This is for unsupervised anomaly detection for streaming algorithm, the IFTM framework. And we try to reduce the CPU resource for all of the 3 algorithms while applying them. So we send through 10,000 samples as file input, 30 dimensions, and it's resource monitoring data from a server, and apply these algorithms to find anomalies. We evaluate the quantitative time needed to process one data point. Here comes the result. On the right side, you see the commodity server, which functions as public cloud. There you see the LSTM network utilizes the most time, which is expected as neural networks normally consume a lot of time, especially compared to these online optimized versions of ARIMA and concept adapting Birch. So you can then decide, is it the data input frequency enough for using these algorithms depending on the CPU cores you have, but also you can check whether you can place even more algorithms on one host in parallel. On the left side, you see the same experiment on the Raspberry Pi. There you see a huge difference between LSTM and both other algorithms. So here you see that LSTM needs much more time per sample, and this might be not efficient anymore for real-time processing. So in this case, maybe the usage of LSTM is not being possible on the edge device, but should be then moved to the cloud. On the other hand, for example, for forecasting, you can use ARIMA and LSTM, both. We have other experiments where you see that LSTM networks are much more or better in qualitative results, like getting higher accuracies, applying the LSTM network than the ARIMA network. So here you can, for example, at the edge, apply in some use cases ARIMA to have some quick response directly from the edge, but then are moving also the data to the central cloud and analyze the even higher quality results from the LSTM network, which might be getting posted then back later and be used then in the edge also. So we have much more projects running utilizing these frameworks. So we have from Huawei the edge computing for smart cities, a couple of projects there, especially in the area of AI ops. Then we have a project with Siemens together about smart factories with KSB, which is a huge industrial water pump supplier, about predictive maintenance, so a typical IoT use case, but we also apply the algorithms and frameworks in the medical field for ECG analysis and ultrasonic sound videos. In the BBC, Berlin Big Data Center, we are researching the task scheduling of algorithms. And for critical infrastructures, we are ongoing projects which are called Water Grid Sense and Optima. Thank you for your attention. If you have further questions, please contact me via email, for example, or visit our homepage. Thank you.